We are continuing our videos on exponents, and today we're going to get into solving exponential equations and something called the change of base formula. So those are the two main focuses of today. This is Chapter 5, Section 7, and it is called exponential equations and the change of base formula, as I mentioned. This will be a relatively short video. And then I'll create some videos after this on reviewing and doing some of the topics that we've done and do some practice problems. Change of base formula. So let's kind of see what we're talking about here and why a change of base formula might be useful. So in the past, we've been able to solve problems like 2 to the t minus 3 equals 8. And we've been able to solve that because we can write them as like bases. 8 is 2 cubed, and now we can say powers have to be equal, so t has to equal 6. Or similarly, we could have 9 to the 2t equals the cubed root of 3 times 3. So 9 is 3 squared, so 9 to the 2t equals 3 times 3 to the 1/3. This becomes 3 to the 4t because we multiply powers to power. Here we add exponents because we're multiplying like bases. And that becomes 3 to the 4/3. And again, we say 4t equals 4/3, which means t equals 1/3. Okay, so the situation arises, well, what if the powers are not the same? Or what if I can't make the bases the same? And we can't really apply any of our properties. So we come into a situation like that, and let's take an example of 5 to the x equals 3 times the cubed root of 4. All right, well, 5 to the x, you can't do anything with that, so we'll leave it as 5 to the x. And this becomes 3 times 4 to the 1/3. No like bases there either. I got to get x by itself. So if you recall, we have a log property that says log base b of m to the p is equal to p times log base b of m. So I look at that and I say, okay, I have to get this out of the exponent. So if I log both sides, if I take a log of both sides, I can say log of 5 to the x equals the log of 3 times 4 to the 1/3. Well, now my exponent can jump to the front, and I have x log 5 equals the log of 3 times 4 to the 1/3. In which case, x then equals the log of 3 times 4 to the 1/3 over the log of 5. And I can use my calculator then to get an answer. So I do the log. It opened the parentheses for me. 3 times 4 to the 1/3. Close the exponent. Close the numerator. Divided by the log of 5. And I get 0.9697 or 0.97. Approximately 0.97. So that's how logs can help us solve things with unlike bases. We can just take the log of both sides and do whatever you need to do. So let's look at an example here. Let's say that in the year 2005, Lower Merion School District had 8,000 students. The trends showed that the population or the student rate was increasing by 2.04% yearly. The newly constructed school district, let's just change that from high schools to school districts. The newly constructed schools in the district can house, let's say, 12,000 students. When will the population exceed the school size? When will the population exceed the school size or the limit? So it's growing by a percentage a year. That means exponential. So we want to know when it will exceed 12,000. We're starting at 8,000, and we're increasing by 2.04%. That's 100% initially, plus the 2.04%. And that's being raised to some time t. That's what we're looking for. Right? So 100% plus 2.04% is 102.04%, which is 1.0204 in decimal form. Okay, so that's where this came from. I added 100% plus 2.4%. Plus 2.04%, sorry, 2.04%. So we're going to go through and solve this. I'm going to divide by 8,000 first. So I get 12 over 8 equals 1.0204 to the t power. And of course that reduces to 3 over 2 equals 1.0204 to the t. And unfortunately, 1.5 and 1.02, I cannot make them like bases, but what I can do is I can take the log of both sides. The log of 3 halves, or 1.5, equals, the t jumps to the front, log of 1.0204, and then I divide both sides. So I get the log of 1.5 over the log of 1.0204. We use our trusty TI-84 calculator. The log of 1.5 divided by the log of 1.0204. And it'll take 20 years for the population to exceed what we're looking at. Whoa, a lot of stuff disappearing there. So 20 years we had said. T is approximately 20 years based on this log equation. All right, so that's how you use the logs to solve some equations. And the last piece of today's mini lesson here is the change of base formula, and change of base formula is awesome. Change of base formula. So let's say we have the log base b of x equals y. All right, now I'm going to derive this formula quickly. This is true if and only if b to the y equals x. That's the definition. Okay, you know that. Well, I want to solve this for y. So I'm going to take the log of both sides. Log b to the y equals log of x. And I can take the log of any side as long as the bases are the same. So you know this is log z, log j, log k. It doesn't matter as long as both sides are the same. Point being, this y jumps to the front now. Don't know why I wrote equals. the y jumps to the front. You get y log b equals log x. And y is log x divided by log b. And again, this can be any base you want. Okay, any base you want as long as both bases are the same. Okay, typically we're going to choose natural log, which is a base of e, or the common logarithm, which is a base of 10. How is this helpful? Well, let's say we want to do log base 7 of 21. I can't do 7 to some power equals 21. It doesn't help me. And, you know, this is a little antiquated now because a lot of our calculators can actually handle writing this, but before you weren't able to do that in our calculator. I can now do log 21 over log 7. Log 21 divided by log 7. And there's our answer, approximately 1.56. And this is our change of base formula here. Let's put this together. We have the log base b of x equals y, and y is the same thing as this. So the log base b of x is equal to the log of x over the log of b. That's your change of base formula. Have a good day. It was nice having you here today.